So thanks for coming to the last lecture. I'm going to talk about the Hamiltonian simulation algorithms, which are post-Trotter. So as I said, so we just talked about Trotter-Suzuki decomposition. And what's nice about it is that it's very simple and intuitive, but there are better methods out there. And I'm going to tell you the basic ideas behind these methods. So let me give you some histories, actually. So for a long time, Trotter-Suzuki decomposition was the default method to do Hamiltonian simulation in quantum computing. But starting around 2010s, an entirely new and different set of ideas started to appear, which seems like very unnatural from the physics perspective. So from the physics perspective, you would think that if you want to implement time evolution, you would try to just emulate nature and just apply infinitesimal version of the time evolution very accurately. But these new approaches they essentially work by applying effectively applying a non-unitary operation, which seems like a very strange thing to do. So unfortunately, reviewing all of these things are well beyond the scope of this lecture. So I won't be able to get into a lot of details. But what I will try to do is to explain the key ideas behind the state-of-the-art algorithm known as the qubitization. This is a very important algorithm that was discovered by Lo and Chuang in 2016. And this is pretty much the standard for any Hamiltonian simulation algorithms. So to explain how these things work, let me begin with a guiding example. So what I would like to do is the following. So let's say I have an arbitrary quantum state psi, here's psi, and what I want to do is that I want to apply a non-unitary operator O to the state psi. The question is like, can you actually even do this? Is this even possible? To that end, let me make a few observations. The first observation is that any 2x2 matrix can be written down as a linear combination of some unitary matrices. Specifically, we learned about these Pauli matrices yesterday. So let me remind you, I is an identity, X is X, Y is Pauli Y, and Z is Pauli Z. And they have the identity is obviously unitary. And X squared, Y squared, Z squared, they're all identity. So all these matrices are actually unitary matrices with squares to identity. Okay. So and the thing is, for a 2x2 matrix is defined in terms of 4 parameters. And here you have 4 parameters: alpha I, alpha X, alpha Y, alpha Z. And moreover, this I, X, Y, and Z in the space of bounded operators acting on 2-dimensional Hilbert space forms a complete set of orthonormal bases. So you can actually write down any 2x2 matrix as a linear combination of I, X, Y, and Z. So that's the first observation. The second observation is the following. So suppose, ultimately we want to apply some non-unitary operator to a single qubit state, but suppose we introduce some extra degrees of freedom to help our goal, okay? And I'm going to introduce another system, which is a 4-dimensional Hilbert space, and their basis states will be expressed as I, X, Y, and Z. So just think of this as like a 4 orthonormal bases of some Hilbert space. Okay. And I'll just write down this particular state called alpha state. And what I'm going to do is the following. I'm going to apply the following unitary transformation called controlled U. And this controlled U acts in the following way. If the state on the first ket is I, it does nothing. or equivalently, it applies an identity operation, which is doing nothing really. And if it's X, it applies the X operation. If it's the Y state, oops, it should be X. So if it's a Y state, it applies Y, and you can guess what's going to happen if we start with Z state. It applies Z. So suppose we apply this controlled unitary to the following state. Alpha tensor, arbitrary single qubit quantum state psi. So by linearity, we can just write down what's going to happen to this thing, and that is the following. Okay. So and so far, no rules of quantum mechanics was violated. We defined the unitary transformation, and we applied that unitary transformation on the system. So one is a qubit, and other is ancillary system, which is helping us in some way. So I'm going to keep that information and move on to the next slide. So now what I'm going to do is that I'm going to measure this thing. So let me draw a circuit diagram actually. So far what we're doing was this. So we start with the two states, alpha and psi, and then we apply the control unitary operation. And then what I'm doing is that I'm measuring this state in some basis. And that basis will include this state, a uniform superposition of x, y, I, x, y, and z. Okay. And I'm not going to even write down the other basis states because I don't really care about them. But certainly, like you can choose a basis that includes this state as one of the basis states. This is like perfectly allowed thing. And I'm going to ask the following question: like, what happens? So suppose we performed this measurement, and suppose we obtained this measurement outcome. In that case, what happens to this part, to the single qubit state? That's the question that I'm asking. And we know what the rule is to compute the post-measurement state. What we simply do is that we apply the broad version of this thing to this state. And let me remind you that this is exactly equal to that. So here we have an exact expression for this state. And if we apply this, then what we end up with is essentially 1/2 alpha I psi plus alpha x, x psi plus alpha y, y psi, alpha z, z psi. And we can, of course, rewrite this as alpha I plus alpha x, x, alpha y, y plus alpha z, z, apply to psi. Okay? And that is exactly equal to 1/2 times alpha psi. Of course, then you're going to have to normalize it. So essentially, we after the normalization, we see that we obtain the state that we actually wanted. Of course, there's a caveat. The caveat is that this happens only when the measurement outcome happens to be this. There is a probability, there is a non-zero probability that you measure something else, and when that something else happens, you will generally get a different result. So this is so with some probability, you can apply a non-unitary operation. So that's the main lesson here. So even though in quantum mechanics you're only allowed to do let's see, unitary transformation and measurement, by combining them together, you can apply a non-unitary transformation with a non-zero probability. And this is okay because you do not succeed always. Sometimes you will fail, and this is something that you can perfectly do well in quantum mechanics. Any questions about this? If not, I'll move on to the next part. So that was the main lesson. And so in light of this fact, we can sort of have some guesses on how you can apply how you can carry out a Hamiltonian simulation. So here's a approach that roughly describes how the state-of-the-art algorithms work. So suppose you have this time evolution operator, e to minus iht. Like, one thing that you might try is that you perform a Taylor expansion and then truncate the sum to some finite order and somehow find ways to implement this non-unitary transformation, because you have to apply, let's say, if you truncate this expansion to some finite sum, you presumably want to do something like this. So maybe you want to find ways to implement mapping psi into h applied to psi, and take some linear combination and maybe post-select. This is something, this is very vague, and I'm going to explain to you in more detail how these things actually work, but that's something that people do at a high level. But at least, like, faced with this high-level description, there are some problems that you can probably see. One is that it's actually not clear how you would implement this operation. So if somebody gives me h, if you give me an h, like, how would I actually implement this transformation? Okay, so that's one thing. And the second is a more serious issue. The issue is that this operation is not determinate state. Like applying a non-unitary transformation to a quantum state is not going to succeed all the time. Like, sometimes it will fail. So suppose you want to, for example, apply h raised to the power of n applied to some state. Then, well, maybe if n is 1, with some probability you will succeed. But if n is 2, the success probability will probably decrease by, so if the success probability for the case of n equals 1 is like p, maybe the success probability for n equals 2 will be like p squared, and then n equals 3, it'll be p cubed, and such and such. So it seems like this will just not work. Yeah, question?
When you mentioned this operation will not be successful, what do you mean by the successful and the not successful here?
Yeah, so for example, in this case, if I end up measuring this thing, this state, then I successfully applied the operator O to the state psi up to normalization. But when I do not measure this state, measure something else, then generally I'll obtain a different state. So in that sense, this is not successful.
But
And yeah. Mm.
sorry, aren't you assuming you apply this operator O acting on the alpha state? Maybe I didn't
So
understand why it fails.
right. So I guess let's see. So what is the let's see. Uh, so there will be like a this Hilbert space spanned by I, X, Y, and Z is a four-dimensional Hilbert space. So If it's a legitimate measurement basis, we'll have to have three other basis states. Let's call it as psi 2, maybe phi 2, phi 3, phi 4. And so when we perform measurement, we could end up measuring this state or that state or that state or that state. But the post-measurement state, for example, let's say I ended up measuring this thing. This will generally not be equal to like O applied to psi times some constant. That's what I'm saying. And there is a non-zero probability that you will measure this state phi 2, right? So there is a non-zero probability that you will not get something that you want.
So you're saying that this the alpha state is not the, so your vector space is not fully expanded by these state, or maybe.
So the alpha state is some state. I mean, it's just some state that I initialize. So let's look at the circuit. So we start with alpha state, which is a legitimate state in a four-dimensional vector space, and psi, which is an arbitrary state. Apply the unitary transformation, and then I measured. And depending on the measurement outcome, I would have succeeded or failed. And to be clear, this is not an alpha state. This is another state. Okay, and I'm just saying that there are four possible measurement outcomes. I'm going to call it as phi 1. So phi 1, phi 2, phi 3, phi 4. There are four possible measurement outcomes. And we can ask whether this is a success or not. This is yes, no, no, no. And we can ask what's the probability of each measurement outcome. And that's equal to, let's see.
Oh, okay, I see. I see. So it's given by the product of the P2 states. Okay, I see.
Yeah. Right. Yeah, good. So this is actually pretty important.
This is clear now. Yeah.
It's good. Yeah, so this is actually pretty important. So if there is any question, I would, yeah, I would really, yeah, please let me know. If not, I'll move on to this other part. Okay, so yeah, so the point is there is some probability that this will fail, and that is obviously an issue. Okay, so later I'm going to tell you how to fix that problem, but for now I'm going to start with this part. So how would you actually apply this transformation? Now, to be clear, what I really mean by this is a normalized version of this. I'm being a little slow here. So it turns out that this problem is actually not too difficult. So I'm going to assume that the Hamiltonian that we care about can be written down in a very nice way. So what I mean by nice is that it can be written down as a sum of terms, which is a linear combination of the Pauli matrices. So here, Pauli matrix doesn't just mean Pauli matrix for a single qubit. It can include Pauli matrices over many qubits, let's say n qubits. And why is this a good choice? Well, okay, so to be clear, this won't be a great choice if you want to simulate the harmonic oscillator, for example. So it's not like a recipe for everything, but at least it's a good choice for locally interacting, let's say, quantum spin models, which condensed matter physicists care a lot about. And also, if it's a system that is consisting of fermions, there's a mapping that maps fermions into quantum spin systems. And after you do that, for most of the constructions that's in the literature, you end up getting a Hamiltonian of this form. So it's a kind of form that covers a lot of cases. So this is the starting assumption. Okay, so, oops, typo. To realize, let me remind you that what we want to do is that we want to apply this transformation. So to realize that, there is a very famous framework that pretty much everyone uses these days, and this is a framework called select plus prepare. As the name suggests, this actually boils down to two subroutines. One is called as select operation, the other is called as prepare operation. Both are unitary transformations. And what they do is very simple. So select, as you can see, is basically applying a conditional Pauli operation. So you look at this first register, and this you can think of this as an index set. And if the index set is I, so let's say I is equal to 1, then I apply Pauli P1, which is the Pauli of my choice to the state psi. If I is, let's say, 2, then I apply P2 to this psi. And prepare is basically preparing some version of the alpha state. So preparing some arbitrary quantum state. So you might be wondering, like, how do we actually construct these things in practice? So here I'll start with a very basic example. So let me remind you the select. Works in the following way. And to be clear, implicitly what we're thinking is that if I were to actually construct this select operation, I would first need to write down like a table like this. So here would be I and PI. So I would be like 0, 1, 2, 3, 100 or something. And PI will be something like X1, X2, Z1, Z2, Z1, Y3, X4, 100, or something like that. So you first need to write down very explicitly the list of Paulis that you're going to use. And those Paulis are going to appear in this Hamiltonian. So you write down the Hamiltonian, and these PIs will be the individual terms that appear in the Hamiltonian. Okay? So that's the first thing that you do. And okay, this is what you're essentially trying to achieve. So how does that work? The simplest version of this is a very simple lookup table. So it's sort of similar to what we discussed last time. So it's a lookup table that only contains two possible values. So if it's 0, then I apply identity. If it's 1, then I apply some Pauli P. So pictorially, this will look like something like this, where the top thing is the control register. Okay. So how do you do that? Well, it turns out that for any Pauli P, you can rewrite it as a conjugation of some single qubit operator, let's say X, by some Clifford unitary C. And moreover, this Clifford unitary C can be chosen to have at most like a linear number of gates in the number of qubits. So if you're curious, I would love to tell you more about this, but if you accept that fact, then what you can do is a very simple thing. So what you would do is that you would simply have a C0 gate. and you will conjugate this C naught gate by this C dagger, by this Clifford. And why does this work? This works because if you plug in the zero state here, that doesn't apply anything. And indeed, if you plug in zero state here, this C naught operation doesn't really do anything. So in that case, C and C dagger cancel out each other, giving rise to identity as expected. But when the first qubit is in the one state, then you apply P. In that case, you apply X conjugated by C, which is exactly equal to P. So select operation, at least for this simplest case, you can implement this very straightforwardly. What about some other cases? What if we have like more than 2 Paulis? Well, to that end, let me give you another example of the lookup table. So this is a lookup table in which, so this lookup table is specifying in terms of some bit string. And for everything, you get identity, except for a single bit string. If all the bits are in 1, then I apply this Pauli P. So how would I do that? Well, that's also very simple. So this is essentially changing the control Pauli into the version in which you have many control bits. So all these black dots are controls. And what should we do? Well, it's the same idea. So instead of having a controlled NOT gate, you have a multi-control Toffoli gates, which is sandwiched by C and C dagger. Yeah. So yeah, if you have a more complicated looking lookup table, before you apply this control gate, you simply flip the sum of the bits. And that way you can just fill up the entire lookup table one by one. So select is like a very simple operation that you can straightforwardly implement using this method. What about the prepare? So the goal of the prepare is to prepare this arbitrary quantum state, which encodes information about the coefficients of the Hamiltonian. So this alpha, let me remind you, was appearing in the decomposition of the Hamiltonian. Alpha was simply this state. Okay. I can only tell you, so this part is a bit more complicated, so I will just tell you that there is a solution to this. So people know how to construct an arbitrary quantum state like this alpha state using like a 1 and 2 qubit gates. And the complexity scales as big O of like n log n divided by epsilon, where n is the number of non-zero values of alpha highs. So there's a well-defined procedure to do this. And so how do we actually realize this? Well, we can do that by using the following circuit. You begin with an alpha state. Then, I'm sorry, I think you're not supposed to start with the alpha state. You start with the zero state. And then you apply the prepare operation so that at this point, you have an alpha state. Then apply the select operation. And then prepare inverse, and then measure. So what happens? Well, let's try to analyze what happens. So you start with the all zero state, tensor product with psi, and then you apply the prepare operation. So you have alpha tensor psi. Then you apply the select operation, and what you get is the following. And you apply the prepare dagger and then measure. But instead of applying the prepare dagger operation, what you could simply do is that, let me remind you that this is alpha. Therefore, the raw version is simply the following. So we can view this, both of these things together as this part, which is alpha. So once you do that calculation, what you end up getting is the following. And of course, J and I, their inner product is 1 only if J is equal to I. And therefore, this is equal to I alpha I pi psi. So, okay, so one thing that I forgot to mention is that without loss of generality, I'm going to assume that alpha i's are non-negative numbers. And the reason why that's possible is because, first of all, I'm assuming that H is a Hermitian matrix. So alpha i's can be chosen to be real because pi's are Hermitian matrices. And then you might ask, like, why can't I choose alpha i's to be positive? Well, that's because pi's can be like a plus and minus like Pauli's, and therefore I can simply choose. So if alpha I is a negative, I can simply choose, like, redefine that Pauli to be the negative version of that, thereby making alpha i's to be positive numbers. So in that case, if alpha i's are all non-negative, which is possible, this just becomes alpha I pi psi, which is exactly equal to H applied to psi. So you can see that with these two simple operations, maybe simple is not a great word, but two operations which are very well studied and highly optimized in the literature, you can make this operation. You can apply a Hamiltonian to a system, not an exponential, not the time evolution of the Hamiltonian, but the actual application of the Hamiltonian to the quantum state. This is something that you can do. And that's a very important thing because this is what people call as the block encoding of the Hamiltonian. So we say that a unitary U is a block encoding of a Hamiltonian if we take the inner product on both sides by some state, let's say 0 and 0 here, then what results, then what you end up having is the Hamiltonian H. So it's easier to actually just draw this. So remember that in the previous slide we had this. So what we're really doing was the following, right? So we started with the all zero state on this first set of qubits. apply preparation, which is a unitary, apply select, prepare dagger, which is a unitary. So this entire thing is a unitary. It's called as U. And when we take the bra of 0 and cat of 0 on both sides, what we end up doing is that no matter what the input is, we end up applying H to that input. And therefore, what we can say is that if we take this, this amounts to just applying, this is the Hamiltonian H to an arbitrary quantum state. And select and prepare provides a very natural framework to implement this like block encoding of H. So I think that's kind of cool, but the real reason why this is important is because this is the starting point of the technique called qubitization, which is the state-of-the-art algorithm for Hamiltonian simulation. So I would like to move on to explaining what qubitization is, but this is a good time to maybe pause and answer some questions. Let me know if you have any questions. Okay, so yeah.
Does this method require more ancillary registers compared to the previous ones?
Yes, the answer is yes. Compared to the Trotter-Suzuki method, which does not seem to require ancillary qubits, this does require more ancillary qubits.
So then practically, is this method still doable calculations, or is this a very expensive calculations?
It depends on what you mean. So like for near-term quantum computers, you probably don't want to use this method, but I should point out that the extra cost is very minimal because you see, like this part, the main question is how many qubits do we need on this blue part? Because the psi, that's the state of the system that you want to simulate. And this depends on the dimensionality of the alpha state. So what was alpha state? And that was basically determined by the number of non-zero terms in the Hamiltonian. So like if you have a locally interacting quantum spin systems, for example, then the number of terms will be like O of n, where n is the system size, usually, unless there's some long-range interaction. And so number of non-zero elements, not non-zero coefficients would be O of n. And that means that it suffices to choose this blue thing to be O of like log of n, right? Because you can store like up to n using log n bits. So we don't actually pay too much for this extra cost. So it is true that we need more, but it is like subleading in n. And in practice, it's also very small, like 10 or 20. Actually, like more like 10 or 5. Okay. There are no other questions. Let me move on to the qubitization part. Okay, so I gave you this high-level explanation on what people are doing, but there are two issues. One issue was that it wasn't clear how we would implement this psi going to h psi, but now we know it. But the second issue was that this operation of applying h to psi is not deterministic. So if you want to apply h many times, then the success probability will probably decay exponentially. So how do we deal with that? So Qubitization basically solves this problem. And to explain the key ideas behind this, I will make a simplification. So far, I showed you very explicitly that we have a unitary U, which is a block encoding of H. So I constructed that using select and prepare operation. And it should be noted that generally speaking, when you do that, U square is not an identity. Okay? So let me be clear about that. But I'm going to assume that we can somehow guarantee that U square is an identity. So you might be thinking, like, why am I doing this? The short answer is that it's because it simplifies my analysis. But the more serious answer is that even if you're given a unitary which block encodes Hamiltonian like this, such that it doesn't square to identity, there's a general procedure to convert that into a unitary which for which block encodes H and actually squares to identity. So like you can always guarantee this. And what's better, you can actually the number of extra qubits that you need is like very small, like 2 or something. And the number of gates, the extra gates that you need, like it blows up only by like a constant factor, like a factor of 2. So in the grand scheme of things, this doesn't really like add too much cost. So it's safe to assume that if you constructed a unitary, which is a block encoding of H, there is another unitary U prime, which block encodes H, and it squares to identity. Okay. So that's going to be my starting assumption. And there will be another simplification that I'm going to make my analysis easier. And this is, I'm going to assume that the ancillary qubits, you can see that I wrote like A here, that means ancilla, like the extra qubits that you need. I will assume that that number is 1. Again, this is not an issue. So in practice, unlike the previous simplification, the number of ancilla qubits will be generally larger than 1, to be clear. But the math that I'm going to do in the next few slides will basically carry through, like with a very minor modification. So let's say the number of ancilla qubits is like 10. The things that I do over the next few slides will just carry over naturally to that setting as well. So with that, I think I'm ready to show you how the qubitization works. So let's suppose we have a block encoding of H. And remember in the previous lecture, when we dealt with Hamiltonian, we found it very instructive to plug in an energy eigenstate. And here we're going to do something similar. So I'm going to apply the block encoding of H to a state where the state is not an arbitrary state psi, but an eigenstate of H. Okay? And that will lead to the following thing. So why is that? It's because of the block encoding assumption. Oops. I know that this is going to be H. So if instead of having an identity here, if I have an energy eigenstate N, I'm going to have like N here. So that's going to be En N. Okay. And you see that over here, I on the left-hand side, I applied like the bra of 0. So I can expect that if I apply U to this thing, I'm going to get En 0 N plus some junk. And to ensure normalization, that junk must have an amplitude of square root of 1 minus en squared. And it's, yeah, so this is some subtlety that I haven't mentioned before, but basically this block encoding, yeah, so yeah, so if you think about it, like if you have like the 0 component here, then what you have here will not be exactly en times n. They'll have some like extra stuff, but you don't have that. So that's why this thing has to be in the one state. And what happens to the remainder of the state? Like it'll be some state that will depend on n, but I don't know what that state is. I'm just going to denote that as psi n. Okay. And the question is the following. So suppose I know how this unitary acts on this particular state, 0 tensor energy eigenstate. The question is, I should note that this is a typo. This is psi n. If I apply u to 0 tensor psi n, I'm sorry, so that's not what I was trying to fix. I was trying to fix this thing. So if I apply this unitary u to 1 tensor psi n, then what kind of state are we going to get? At first sight, this may seem like an ill-defined problem because we don't even know what psi n is. But it turns out that there is an answer to this. And we can get an answer because we assume that the unitary squares to identity. So what we can do is that we can simply apply the unitary u both on the left-hand side and the right-hand side. So let's see what happens then. So on the left-hand side, I get u squared applied to 0 tensor n. And on the right-hand side, I get u applied to these things. And that's, oops, sorry. I think that is correct. So this is what we get. Okay. And this thing over here, this is what we wanted, right? That was what the question was about. And here, this is u squared's identity. So the left-hand side is simply 0 tensor n. What about this thing? The first term over here, well, we know the answer to that as well, because we wrote down an expression. So that's simply en squared 0 n plus en squared 1 minus en squared 1 psi n plus. So we arranged everything by moving this guy over here, moving this guy to the left-hand side, and thereby we get this nice relation. That's an important relation. Okay. Any questions so far? So an important lesson from this, and this is actually it's a very important observation. And the observation is that there is a two-dimensional invariant subspace spanned by the action of u. And that subspace is spanned by these two vectors, 0 tensor n and 1 tensor psi n. And I think this is really cool because the thing is we don't even know what this psi n is. Nevertheless, just because u squared is identity, we were able to identify the existence of this subspace. Moreover, on this subspace, u acts in a very particular way. So let me just flash you back to the previous slide. So we have two states. So let me call 0 tensor n, 0 tensor n, 0 tensor n. Yeah, 1 tensor psi n, 1 tensor psi n, 1 tensor psi n. So you can see the 2 by 2 matrix, the action of unitary on this two-dimensional subspace is obviously a 2 by 2 unitary matrix, and that unitary matrix is this thing. And what you can check is that this actually squares to 1. So on the two-dimensional subspace, there's another unitary that we can very easily apply. And this is a single qubit unitary, e to the minus I z theta, acting on this qubit. You see that 0 and 1. So obviously, this unitary acts as just a like a 2 qubit rotation matrix. And its explicit form is like this. So what we can imagine doing, the gist of the qubitization is the following. So let's try to apply these two kinds of operations. So pictorially, what we have is the following. So I'm going to use two different colors. These orange colors means these single qubit gates. E to the minus I z theta 1, e to the minus I z theta 2, e to the minus I z theta 3, e to the minus I z theta 4. And this other thing, let's try one more time. Good. It's a different color for this. And this is really the unitary U. U was the block encoding. Of H. And we have plugged in a quantum state like energy eigenstate N. Getting an energy eigenstate N back out. So, sorry, so there. So that's what we're doing. And the thing is, when we keep on iterating this thing, we essentially we are restricted to this two-dimensional subspace, and the action of these unitaries, once you reorganize everything, it turns out to be in this very nice form. So it still has to be a 2 by 2 matrix, and it has to be a function of the energy eigenvalue En, and it's of this form. So both P and Q are polynomials of certain degree, and this is the general expression. So what did we do so far? So what we did was the following. So we considered this very simple looking sequence of operations involving a single qubit rotation and a fixed unitary, which is a block encoding of some Hamiltonian. And if your input is an eigenstate N, then we realize that on the two-dimensional subspace, this entire thing acts in the following way. So here's the question. The question is, suppose you believe all of this, which is true. We can explicitly verify it through calculation. And suppose we apply the same sequence of unitaries to this state 0 psi, where psi is an arbitrary quantum state. And then you measure the ancilla qubit and measure 0. Okay. So that amounts to picking out this a top left corner of this 2 by 2 matrix. Then the question is, what is the post measurement state? And the answer to this is very simple. Well, so what we established is that if we start with the n tensor 0. Let me just go back to the previous slide. Yeah, I guess the setup was that 0 tensor n. So 0 tensor n. Then what we're going to end up having is p en pi q en this is the unitary transformation that's going to act on that 0 tensor n. And then we're going to measure the first qubit in the 0 and 1 basis. And if we measure 0, we're just going to have to contract. We're going to apply the broad version of 0 from the left. So then what do we get? We are simply getting P of En. And so what happens if we start with the most general quantum state psi? Well, let's just expand it into the energy eigenstates. Okay. And then if we go through all of this, we get this factor of AN, P, N, PEN, N. And the thing is, P is a polynomial. And therefore, this is exactly equal to P of H applied to N. And of course, we can pull out this P of H to get that, which is P of H applied to an arbitrary quantum state psi. So what we found is that if you go through this procedure of applying a, let me just emphasize one more time the simplicity of this circuit. If you apply single qubit gate U of H, single qubit gate unit block encoding of H, single qubit gate block encoding of H, you end up getting a polynomial transformation of H on an arbitrary quantum state. And you didn't suffer from this exponential decay of success probability problem. Like the success probability is exactly equal to the norm of this vector, and so this so that's it. So you have something that looks very nice, and this was so I think that's like a very mathematically nice observation, but what's even nicer is that this is actually practically very useful. So we now have a very general framework to apply a polynomial transformation to the Hamiltonian H and apply it to an arbitrary quantum state. And there are two important facts. First is that for any real polynomial, as long as if P of X is like too large, obviously this is not going to work. If it's like smaller than 1, by just choosing a different measurement basis, we can apply this like P of H. So you don't need to worry about this like mysterious function like polynomial Q of X. And the second thing is, given a real polynomial P of X, there is an efficient classical algorithm that computes the set of angles that are used in this like single qubit unitaries, right? If you think about it, there is a fixed unitary, which is the block encoding of the Hamiltonian, and there's a variable unitaries, which are the single qubit rotations. And the shape and the precise polynomial is determined by this angles. So you might ask, given a polynomial, can I actually obtain these angles somehow? And I'm saying that the answer to this question is yes. And there's even an open source software that solves this problem. So if you have a good polynomial approximation, this is the real important part. If you have a good polynomial approximation of any function that you want to apply to your quantum state, so let's say f of h, then you're in game to use the qubitization. And this application of qubitization is not just confined to Hamiltonian simulation, but this is one such example. So to be concrete, let me show you how this works. So if we were to use the framework of qubitization, our goal is to apply e to the minus iht. So the function that we're going to use is e to the minus ixt. So that when we apply f of h, this will be e to the minus ht. And to that end, you can use what is like known for a long time, called like a Jacobi angle expansion. So the basic idea is that you use Euler's formula for this. And you realize that cosine xt can be written down as a sum of polynomials, and sine xt can be also written down as a sum of polynomials, where these things are known as like Chebyshev polynomials, Bessel functions, basically some special functions and special polynomials that have been very well studied. So what you do is that you simply plug in these results, and this leads to a complexity of that scales linearly with t. And unlike the complexity that you saw in the Trotter-Suzuki decomposition, something that scales logarithmically with 1 over epsilon, where epsilon is the inverse precision. And I should note that this is optimal in all the parameters in terms of time and inverse precision, and even the norm of the Hamiltonian. Good. So, yeah. Yeah, so I guess that concludes the final lecture. So what I wanted to say was that the state-of-the-art method for Hamiltonian simulation uses like a very non-intuitive backstory to physicists, namely applying a non-unitary transformation to an arbitrary quantum state. And I think it's pretty cool that this method actually outperforms the so-called more physical method, such as the Trotter-Suzuki decomposition. And a side remark is that the quantum computer, in light of this qubitization technique, seems to be very good at applying lower polynomial of the Hamiltonian to an arbitrary quantum state. So it's a very natural thing to think about. Like quantum computers are not just good for applying time evolution, it's also good for applying some polynomial transformations of these matrices. So it'll be interesting to think about the applications of this observation. Okay, so thanks for listening. I still have some time, so if you have any questions, not just about this lecture, but all the lectures, I'll be happy to answer.
Thank you. So, question from the room here. Or in Zoom. Okay, so I have a very generic question. So the first question is that for the application of this Hamiltonian simulation. So yeah, I checked this the cited paper here that you cited, and then there are a bunch of some chemistry and the condensed matter. So my question is that is this Hamiltonian simulation that you introduced, is it any that application that you can talk to us in a simple and easy way, how we can or some application in the actual application in the other field?
Let's see. Let's see. I guess it depends on what you want to compute. But I guess the simplest thing is maybe you want to prepare. Maybe you want to prepare the ground state of your system, and then measure correlation functions. And the best method for ground state preparation is based on quantum phase estimation, which is based on Hamiltonian simulation. So it's I guess that would be one application. Okay, so what I just said is not exactly true, actually. So the current best method for quantum phase estimation does not necessarily need Hamiltonian simulation. But that said, I guess like if you're interested in dynamics, it's just a very natural thing to do. Yeah.
Okay, so I have a concrete question. So
Mm.
I heard about some Ising model. Then
Mhm.
I wanna, okay, for example, I want to try to minimize some function. Then I
Mhm.
can put this function in terms of the Ising model.
Mhm.
Then because you talk about the current state of the Hamiltonian, can I use this Hamiltonian simulation or quantum phase estimation to get the global minimum of the function that I'm interested in?
Probably not. At least not in an efficient way, because you shouldn't expect there to be any method that uh, that that finds the ground state energy in an efficient way. Because like if you can do that, then you can solve any NP complete problems, but nobody expects that's possible.
So maybe another way of asking the same question is what kind of problem might be the useful problem for this particular Hamiltonian simulations? What kind of questions we should be asking, which are appropriate for these Hamiltonian simulations?
I guess like the most natural like application that I can think of is the screen function calculation. But I think that's like the simplest thing that I can think of. But other than that, uh, yeah, I'm not sure actually. So like that's usually what people say is that, well, like you're interested in you're usually interested in yeah, what are you interested? You're interested in like computing correlation functions or dynamics, and that's usually the end of the discussion. Unfortunately, I don't have much more to say than that. But yeah, yeah. So I'm not sure. I am not sure.
Yeah. Okay. Thank you.
And I was a generic question.
Mhm.
So I think that most of students here, and this is the really first time to heard about the quantum information, quantum computing. And then if they are interested in they are maybe they know that very well-known book Iren Chang, which is very big.
Mhm.
So, so do you have any good and good references for the student here?
Mm, I guess the Prescott lecture notes are pretty good.
Prescott.
Yeah. Um, so there are, I think those two are like good references still. Yeah. There's a textbook by Mark Wody, like it's more on the information theory side, but still, I think it's a good reference because it contains everything. It's not really much about quantum computation, but I still think it's very useful.
And another very naive and a simple question is that in the US part,
Mhm.
okay, so in our field, there are some attempt to consider the quantum computing and quantum information in our high energy physics. And do
Mhm.
you have any discussion or contact or some emerging collaboration in the United States for the high energy field and the quantum computing or quantum information?
So it's not something that I personally work on, so I don't have a very detailed answer. But I've noticed that people started to think more serious about simulating quantum field theory using quantum computer. These seem to be actually very serious works. I know some people who work on some like near-term implementations of these, like let's say Trotter Suzuki decomposition of some like lattice gauge theory, for example. Yeah, those are the things that I see on arXiv, but yeah, I'm not sure how beyond that. I don't know.
Okay, thank you. So, is there any question? I want to ask a really naive and bad question. Before I want to ask a question, can I just turn off the record? This is off the record question, so I don't want to be recorded. So please stop the recording. Thank you very much. And okay, bye.
Right.